Wait, how do I stop sharing my? Oh, and also thanks so much for everyone for attending the USACO Bonds class. Yeah. Okay. Bye.
Okay. Let me share my screen on this end. Oh my gosh. All right. I hope everyone's doing well. My name is Andy. I'm one of the founding officers of Kid Teach Kid, and I'm also the president of operations. And today I'm going to be talking to you guys about USACO Silver, specifically binary search and prefix sums, which are two great algorithms that I think everyone should learn if they're first starting out in USACO. USACO Silver, I mean. Okay, I won't be presenting, so I can write on the screen. But let me know at any point if you guys can't see my screen. And I will try to keep the chat window open. Yeah, I'll get to the Google Classroom. Okay, so hey everyone, this is the USACO Silver course. And through this course, you'll be learning about a lot of the algorithms that you need to succeed in this division. And at the same time, hopefully it helps you strengthen your coding and problem solving abilities. And we'll be using Java like the other class. Okay, so here is the Google Classroom link. And I guess actually before we move on, I do have a handout that I'd like to share with everyone. So let me download this, and then actually I'm able to attach a file to the Zoom chat. So here we go. Can you guys let me know if you can see that and download it? Okay. Oh, I sent it to panelists. Sorry. Okay. So I've sent that. You really don't need to print it because it's 11 pages, but I think it's pretty good to have pulled up if you're trying to follow along. Oh, okay. Well, that's annoying. I guess, can everyone try joining this Google Classroom? That is the code. And since that's not working, I guess I'll just, I will just upload this as an assignment. Sorry about that. Okay, so while that uploads, basically this class will be going over the lesson on this PowerPoint and through the handout. We'll be doing some example problems, and then we will try some USACO or LeetCode problems. LeetCode is just another website that has a lot of great coding questions. Yeah, let me go back to the class code. Okay. Our schedule is pretty much just learning about algorithms most of the time. And then on week 3, we'll be doing some stuff with data structures. So it's going to be a bit more geared towards like the actual Java side of it than the algorithm side. But hopefully once we go through the first 2 weeks, you'll be more familiar with Java if you're not already. Okay, just a few prerequisites that I recommend, but of course, if you're doing this course as well as the USACO Bronze course, you should be fine. So you want to know import statements, so that's like util and IO. These really aren't too important, and I'll show you guys what they do anyways. Variables like declaring and initializing them. Conditional statements like if else statements, loops, for and while loops. Arrays and array lists are pretty much the only data structures that you need to know for weeks 1, 2, and 4. And we'll be doing a lot with arrays today. Classes you really don't need to use. I put it there just because it's like something that sometimes shows up in USACO Silver, but we really won't be talking about it too much. Methods, we will see a method today, but these are basically functions and you don't really need to know too much about them either. And then input output, we won't see today, but it's something that you have to know for USACO Silver, or all USACO levels actually. Okay. So if you've joined the Google Classroom, you'll see that there is already a handout that's up there called Handout 0, and that tells you how to set up Java and Eclipse on your computer. So if you want to like after class do the homework assignments, then you should have an IDE set up. And an IDE is basically an application that helps you write, compile, and run your code. And without it, you can't really like write Java files. Yeah, the Google Classroom link, you can join the Google Classroom using the code. I'll send it again. Okay, let's see. So if you have this handout pulled up, that's great. And I think it's pretty helpful to have this in another window so that you can like look at the code, look at it in a holistic manner. And there's also like code segments here, so it's easier to follow along with. That said, though, I will pull up Eclipse right now. I wanted to get rid of it for now to see to show you guys like how to pull it up. So I just go to Eclipse. Actually, this may be a wrong version. Should be this one. So this is what you should end up with after you follow Handout 0 to get Eclipse. This is the workspace that they provided me with. I really don't do anything. I just click launch. Okay, it's launching, and then within this workspace, you can create classes, and within these classes, you can have like main functions like this one that can actually run your code. So to demonstrate how to make a class, I will try to open this up. There we go. Right-click source, go to new, and then click new class. I'll call this binary search. And I will create something called this stub, which is a main method. And whatever is in this main method will run when I click run. So that opens up. I'll get rid of this. Okay, so back to the PowerPoint. Binary search is actually kind of like, it sounds like a super complicated topic, but it's actually not too hard to understand. And I say this because when I was in 8th grade or 7th grade, I heard binary search and I was just way too scared to like learn about it because it sounded like such a complicated algorithm that needed really complicated code. But what it really is it's an algorithm to find some element within a sorted array of elements. So actually, I'll go to that later. Let's say I'll just like make a random list of elements. Again, sorted is pretty important. Your list has to be sorted in order for you to do binary search. So this is a list of elements. They're pretty random, but you might recognize them as the primes less than 20. And binary search is something that lets you find the position of any element within this list. So like if I try to do binary search and find 5 within this list, then I will end up returning 2. And it's 2 because, let me label the indices real quick. In Java, Python, and C++, indices always start with 0. And if you were here from the previous class, you may remember that. So 5 would be in index position 2. This is index, and then this is value. Of course, I would store this as an array. So it's not technically a list. So another example, if I try to find the location of 7, I would return 3. And then what I want my binary search algorithm to do is if I put in like 6, if I try finding 6 within this list, well, it's not here. So I want this to return -1. So I want this method to return -1 whenever I give an element that's not actually in the array. So here's kind of how it works. And instead of having a list like before, I'm just gonna kind of draw a line. And let's say this line is just made up of a bunch of dots, but they're too tightly packed for you to see each individual dot. So again, this array is sorted. So all of these elements are in, let's say, increasing order. And let's say the element that I'm looking for is right here, but I don't know that right now. The computer doesn't know that right now. So what binary search does is first make sure the array is sorted. So step 1, sorted, which is true. So you can move on. Step 2 is initialize your lower and upper bounds. I haven't explained what that means yet, but let me just draw 2, actually make it red, 2 red lines here. One is going to be called low, one is called high. And you can kind of think of this as like something that's squeezing your range. So at all times, your target value will be between these 2 bounds. So when we first start off, we really don't know anything about the data, right? So we know that our target value, well, it's somewhere in the array. We assume it's somewhere in the array. So we just let the lower bound be the first element and the upper bound be the last element. Now, so that was step 2. So initialize bounds. Step 3 is let's look at this middle element, and I'll call this mid. To be more precise, mid is the index and not the actual value. But we can like find what value this points to by saying r square bracket and then mid. So that gives us the value of the element at the middle position. So if our target value is less than, or actually, yeah, we don't actually know what our target is. So let me get rid of this and that. So let's just call our target X. Now, if X is smaller than whatever is at the middle, then we know that it has to lie somewhere to the left of the middle, right? Because we know this is sorted in ascending order. So step 3 would basically be making this range smaller. So now that we know that X belongs here because X is less than whatever is in the middle right now, then we can move our high bound over to the middle. So again, this means that our target value is somewhere between this low bound and the high bound. Before we had the whole array as possibly the location for target, but now we've halved the size of we've halved the number of possibilities. So that's kind of where like the word binary comes into play in the phrase binary search. It just means that we're having the data that we're working with each time. And then step 4 is repeat. And I'll say step 3 is update. So step 4 is repeat step 3. Now we can think of this as a whole new problem. We have our low bound here, our high bound here. Target is somewhere in here. So it's actually kind of the same problem now. We're just working with a smaller array. Again, we see what mid is. This time we set mid to be that. And let's say this time X is bigger than mid. That means X has to lie to the right of mid. But from earlier, we know that it lies to the left of high. So it's going to be somewhere, it's kind of messy now, but it's going to be somewhere there now. And if we keep doing this, then maybe we do mid here and it's to the left. Eventually, what it's going to look like is low and high are going to be on top of each other. And at that point, whatever, most of the time low will be equal to high, like the bounds will be the same. And whatever point is at the position of low and high, that is where target is. Do you guys have any questions? I'll give you all like a minute to ask any. I got a great question. What's the complexity of this? So time complexity tells you like how good an algorithm is. If you don't know what it is, that's totally okay. But just to answer this question, it would be log of n, log base 2 of n, where n is the size of the array. If you don't understand what that means, completely disregard it because it doesn't really matter. It's just like, it just tells you how good binary search is. Okay, no questions? Cool. So here's an example. And while I go through this example, I'll also be typing the code into Eclipse so you guys can see like how you guys can get a better idea of how Java works. So let's just declare an array called primes. And it's the same array that we saw before. And once again, we're looking for the location of 5. So I'll just pull up Eclipse. Declare an integer array. So a fixed list of integers. I'll call it primes. And then normally in USACO, you won't be like initializing it. Initialize means you give it values you give the array values. So like this would be initializing it because I'm giving it the values 2 and 3. Normally we would be declaring the array only and giving it like a size. But in this case, to make it more clear and to avoid having to like manually put in each element one at a time, I can like set the, I can initialize this array by putting curly brackets and then typing the elements in. Okay, so I've made the primes array. So we're looking for the location of 5. That's the next slide. So the first solution that maybe worked in USACO Bronze but does not work now is called a linear search. And linear search means going through each element one by one and seeing if it's equal to your target value. So I'd go from 2, see that it's not 5, then 3, it's not 5, then 5. Oh, great, I found it. So while it did run pretty quickly in this example, first of all, because 5 is at the beginning, but second of all, because this array is just so small. Even though that's true, USACO will really only deal with huge sets of data. So your array might be like, your array might have 10 to the 5th elements in it. And it's just way too slow for you to have to go through each element, each 10 to the 5th elements, just to find one target value. So that is linear search. For completeness, I'm just going to show you guys how I would implement it. So I would go through each element of primes. I would be my index that I'm using, and I do this from 0. So from the first element, or from the 0th element all the way to up to but not including the primes.length, so the last, so including the last element. And then I just test if, actually I'll say if target equals 5, or sorry, I'll let target be equal to 5 because that's what we're looking for. And if target equals primes, sorry, is equal to primes at I, then just print out what I is. So print out the location of target, and then I'll just break, oh my gosh. And then I'll just break out of the for loop, because there's really no point of running the whole for loop if I've already gotten to it. So I'll just break. That's great. So before we move on, I'm just going to move all this stuff over to a method. And along the way, I'll just talk about what a method is. A method is a function that takes an input and then returns a value. Public, you don't really need to worry about that. Public means it's accessible to other classes. Static means that I can, it's also kind of complicated to explain, but I can just call it. I can call the method just directly in the main. And then this would be my return type. I'm returning an int because I want to return the location of target. And then I'll just call this method find. Inside of, like, what do I input into find? Well, I would input what I'm looking for and the array in which I'm looking for the target. Okay, so it's giving me an error right now because I haven't yet returned anything. So for now, I'm just going to say return 0. But that's just a placeholder. So I'll copy and paste, or I'll paste what I had from before. I'll actually change primes to R to make it more general. So there we go. So now we have a method that finds target in any array R. And this is a linear search, which is bad. I'll just say that. Oh, and of course, once we reach we reach target in R, we'll return I, the index position of it. And if we end up going through the array and we don't find target anywhere, we'll just return -1. That's like the universal way of saying something does not work. And in the instance of like searching for something, -1 means that it's not in whatever you're looking for. Okay. So if I try find, I'm just going to get rid of target. So I'm trying to find 5 in primes. And I'll print this out. Okay, so if I run this, I get 2. Let me just get rid of this extra print statement. And 2 is right, because if I go back to this list, 5 was in index position 2. Yes, I think there is the problem is like the built-in method either, I'm actually not completely sure if it exists for Java. But if there is one, they can't assume that the array is already sorted. Because maybe I try this for an array like 5, 1, 2, 5, 4, oh, sorry, 5, 7. And if I try to find it, the computer will have to do it using a linear search because there's just no guarantee that my array is sorted. So there's no guarantee that binary search will work. Yeah, I think that's string like index of. I don't think there's one for array, but if there was, again, yeah. Okay, so binary search, we've talked a bit about like how it looks, what it looks like, basically bounds. Then we move the bounds over. We basically squish our target region until we get to one number. Okay, so let's see how that works in code. I'll keep whatever's in the main method because we still want to see if this works. Now, let me pull up the handout because there are more detailed directions like or steps here. So first, make sure that the array is in increasing order. Again, it's kind of hard to like, if we're just writing a method, I don't think it's not worth it to like say, oh, arrays dot sort the array that I'm passing in. Since this array is not changing, I could just go in the main method and then sort whatever I'm putting into the function. But it would be way too slow for me to sort whatever I'm putting in each time. So I'll just do that here. Even though it's already sorted, like if I want to change primes up, then I could do that. Okay, so fine. We were done with step 1 because we didn't have to do anything. Step 2 was initialize and declare and initialize your bounds. So I'll just call it low and high. So the low bound means everything, nothing to the left of the low bound can be a possible place for my target value. The high bound is like same thing but opposite. Nothing to the right of it can be my target value. And when I first start off with a method, it's going to start at 0 and r.length -1 because target value could be anywhere within the array. Yeah, so the question was, what happens if you do binary search but ask to find a number that's not in the set? I think the code is here. So the code that I had earlier was this. And it goes through the array with the for loop. And if it finds it, then it's going to return the position, awesome. But if it doesn't find it, it's just going to go finish the for loop and then return -1 to convey the fact that there is no target within R. Good question. Okay, so I have that initialized. I'll skip to step 4 because step 4 says repeat this, and of course in Java your repeating statements are the loops, and that goes before everything else. So I'll just do while, and we repeat step 3 until either we find the target value that we're looking for, or if somehow, and I'll use a whiteboard for this, somehow maybe my left bound went too far to the right and my right bound went too far to the left, and now this is my low, that's my high. That just doesn't work. But typically that only happens in one case. But that's like how I want my program to stop. So while low is less than or equal to high, so while these bounds still make sense, now I'm going to create a temporary variable called mid, and this is going to be the average of low and high. One thing to keep in mind though is that the average will return low plus high divided by 2 will return an integer. So if like the actual average is 4.5, mid will be set to 4 because integer division uses remainders. Okay. Yes, it's a great observation. So I have mid set, and that was part of step 3. The rest of step 3 is comparing whatever element is at mid with my target. Yeah, that's actually true. I could do while low is less than high, I think. Yeah, that should work. Mm-hmm. Oh, the problem is like actually, I think it makes more sense if I go through the if statements first, and then I can explain why it's less than or equal to. So now compare target with our at mid. So let's say the middle element is bigger than target. That means target has to lie to the left of whatever of the middle element. So to do that, I won't change my left bound, but I will move my right bound, my high bound, over to the middle. Now here's something that's really problem specific. So what do I set my high bound to? Do I set it to mid? Do I set it to mid -1? And it really depends on the problem. In this case, I would set it to mid -1 because if we have like 2, 3, 5, oh. So I start with that and that. Actually, I might as well just show this out. So that's 1, 2, 0, 1, 2, 3, 4. Oh my gosh. 3, 4, 5, 6, 7. So my low would start at 0. My high would start at 7. And then here's my temporary mid. Mid would be the average of 0 and 7, and that would be 3 using integer division. So here would be my mid. And my target is 5. So I know that my search range should be limited to the left half. Now, I've already tried 7. 5 is not equal to 7. So I can actually move my high to 1 before the mid, because I know that the mid doesn't actually work. And the reason I know that is because my if statement only says if the array of mid, the value at mid is greater than target and not greater than or equal to target. So this guarantees that they're not equal, which means that 7 is already out. So I can just move, I can narrow this range down even further to 2, 3, and 5. So high would be updated to 2. And then I would go through the loop again. Once again, mid would be the average of low and high. So that'd be 1. This time, however, 5 is bigger than 3. So I'll write that. And in this case, I can, using the same reasoning, I can move the low to 1 more than whatever mid was. I don't have to move it to mid. And in fact, if I do move it to mid instead of mid plus 1, there's a possibility that you get caught inside of an infinite loop, which is never good. Oh, let me do else if. And then the last case is, well, we've done bigger than, less than, if they're equal to, and that's if target equals the element at mid, then I'll just return mid because that's the index position. So this should work. And the only time I'll be returning -1 is if we break out of the while loop without ever reaching this statement. And we break out of the while loop whenever there's no occurrence of target within R. And I can show this in a bit too. So going back here, mid is 1. So I'll move low now to 1 more than mid. So now low is 2, high is 2. The problem with doing less than only, and the while loop would be, if I did less than, I would be stopping at this point because low and high, the low is no longer less than high. But at this point, I still have not returned anything. So I would break out and return -1, even though the element actually does exist at position 2. So that's why this equals there. And then the final thing is, in the final iteration for the loop, mid would be the average of 2 and 2. So that's just 2. And I test is the element at position 2 equal to target, and it is. So I would be going into this part. I don't know why that went away. Okay, and at that point, what? That is weird. Okay. At that point, this function would terminate because I had already returned something, and I would go back here and it would print out 2. So let's just see if this works by running it. Okay. Oh. I have no idea why I put return there. Okay, great. So it says 2. This code is all in the handout as well, if you didn't get to copy this down. Okay, so we've gone through linear and binary search. Just a quick analysis of like how they compare. Linear search is linear in nature because you have to go 1 by 1. So this is something called O of n. And this means linear. It's a bit hard to explain, but we generally know that log n is less than n. And in this case, specifically, it would be log base 2 of n. Log base 2 of n is almost always less than n. Like, for example, if n is what I said before, 10 to the 5th, like the size of the arrays that we might be given, log base 2 of 10 to the 5th might be something like 15 or 20. But then n itself would be around, it would be 100,000. So this is way, way, way smaller than that. And that's kind of how like binary search would compare with the linear search if we think about this in terms of time. So applications, there are a few applications. So you can use binary search not only for finding a target within an array, but you can also use it to like figure out where I would insert something into an already sorted array. And that's going to be the practice problem that we'll do. It's also used most of the time in USACO for finding a maximum or minimum value that works. So an example is like if you're at the basketball courts and you're trying to shoot a basketball in, you may start off with a lot of power, but then you realize it's too much. Then you go back some, you realize it's still too much, then you go back some, and you keep doing this adjusting thing, which is, although there's a lot more information that you can like, there's a lot more muscle memory involved, and we're smarter than computers when it comes to like figuring out what motion works. It's still kind of like a binary search. Like the idea is still kind of narrowing down what our specific value should be. And I guess this is actually not a very good example because in this case, there's only one value that should work for like shooting a basketball, a certain amount of power that should work. Maybe instead we could say like, I have to throw a ball a certain distance. So I'm trying to find the minimum amount of power that I need to throw the ball that distance. And I think this is one topic, binary search, where the idea of it is actually a bit easier than the coding. And I know the idea wasn't very easy, but the coding is just very, very hard sometimes because there are so many edge cases. So I'll just point out where the edge cases could be. One is here, which was a great observation. In this case, it would be less than or equal to. In some cases, maybe you do just like not equal to, or something besides that. This is another place. So the annoying thing about it is that we can't access like the value at position 4.5. So we have to use integer division. And sometimes what works is actually adding a 1 to this, then dividing by 2, instead of doing this by itself. So that's one thing to watch out for. And the two other parts are just these two lines. You just have to make sure that it's okay to add 1 here, or it's okay to subtract 1 here. You don't want to like, you don't, first of all, or on one hand, you don't want to be stuck in an infinite loop. But on the other hand, you don't want to cut out too many of the values, because maybe you just accidentally cut out the value that you were looking for. Okay, so we'll be trying this problem over here, and I'll explain how I go through it. So if you guys want to take a few minutes to read it, that'd be great. Okay, one thing that that tells you that you're going to be using binary search is target value. Another thing is a sorted array, and then the last thing would be of log n, which tells you that binary search, like a linear search, wouldn't work, and you would have to do a binary search. I didn't realize it would take this long, so I'm just going to go to one of the solutions. And one of the reasons LeetCode is such a great website is because there are just so many solutions to each problem, all in different languages with different like approaches. So here is a Java solution. You can see that the format is very similar to what we had. They first have their bounds. Then they have the while loop and then the mid. And the only difference here is like basically returning this low at the end, because that tells you where the element would go if you wanted to insert it into the sorted array. So instead of returning -1, we would be returning low. Okay. So hopefully we have time for prefix sums. Something about the handout. There's another question called convention, and I'll just open up convention real quick. It also uses binary search, but it's not like the ones that we've been seeing where you have a sorted array. It's more like the third case. It's more like it's more like this third case over here, where you have to find a maximum or minimum value. It is kind of hard, because besides the binary search part, you have to do some little trick that helps you get the answer. But the structure of it will be, I'll just write it here. You'll have like a binary search, like test, like find a value k that works, or find the minimum or maximum value of k that works. And then you input this into a function. And this function tells you whether or not it works. That was a pretty bad explanation, but if you guys read it and want to like start a discussion in the classroom, you can do that to ask questions. Okay. So now we have prefix sums. Prefix sums, I want to say, are a lot more doable than binary search, especially if you're first starting out. So maybe I should have started with this, but that's okay. I wanted to end with prefix sums because next time we'll be starting with something similar to this. Basically, prefix sums tell you what the cumulative sums are for an array. So if I have an array that I start out with, which is 10, 20, 20, 15, 0, -10. So let's just say this is an array that I start out with. And I would be making an array. I would be making an array called psum. Which stands for prefix sum array. And each psum is specific to the array that it's talking about. So I would start with 0. Again, this is an integer array. This would also be an int array. It would match whatever thing I'm storing here. Like if it's a long, then I would do long. If it's a double, I would do double. I start with 0 as my first element in psum, and this will make a bit more sense later. I start with 0. To find the next element of psum, I add these two together, so I get 10. And then I repeat this process. Oh, oops. So at each step, I'm adding the next element in array to the previous element in psum. Now you'll notice, what do each of these tell you? Well, the 0th element of psum is 0. And this says that the sum of the first 0 elements in R is 0. That doesn't make much sense, but it makes sense when we move on to 10. So the element at the first position in psums tells you the sum of the first 1 element in R. And then the second element tells you the sum of the first two elements. The third element tells you the sum of the first three, and so on. And you'll see when we hit the end, 55 is, okay, it's not drawn. 55 is the sixth position, is at index 6 in psum. And that means 55 is the sum of the first 6 elements in R, which is basically the whole array. Let me make sure these values are the ones I used. Okay, I actually used 5 over here, but that's okay. In the handout, I used 5 instead of 15. We'll just ignore that. Okay, so, well, how is this useful? We know the sum of the first I using this p sum. Okay, and let's see how we implement this. So I'll just make a new class. This ends at 5 o'clock. I'll call this prefix sums, and then first I'll declare an integer array. Next, I'll make the prefix sum array. And in this case, I can't hard code it because I want the computer to be doing that. So I just have to give it a length. And if we go back to the slide, we'll see that the number of elements in psum, so 0, 10, oh gosh, 0, 10, 30, 50, 65, 65, 55 is one more than the number of elements in R. So it would be whatever the number of elements in R plus 1 is the length of my psum array. At this point, this is optional, but not necessary. Optional, but it may help you out if this helps you out conceptually. We can set the first element of psum to be 0, but in languages like Java, they automatically set your all your elements when you can declare it like this. They set all the elements to 0. So this would be unnecessary in Java. But in C++, you would have to say, you would have to let the first element be equal to 0. Otherwise, it's going to be some random value. Okay, so we have that. Now we're gonna build the rest of the prefix sum array. And I will do this a total of r.length times, because I do this like adding thing a total of 6 times. And I do this for each element. So going back here, the next element in psum would be the previous element, and then plus the ith element in the base array. So like if we plugged in I equals 0, then the first element would be the 0th element plus the 0th element of R. And that makes sense because psum of I should be telling us, psum of 1 should be telling us the sum of the first 1 elements. Okay, so we have this psum thing declared now. And just an analysis about creating this psum array. It's fast if we have a lot of like queries. Actually, we'll move on to that later. First off, if we have sorry, let me get rid of this. If we go back to the psum array, we have 0, 10, 30, 50, 65, 65, and 55. And let's say we're trying to find the sum of the second to fifth elements in my original array. So I'm trying to find the sum of 20, 20, 15, and 0. And we know that's 40, that's 55 if we just add it ourselves. But how would we use our p-sum array to do that? Well, this tells us the sum of the first 0 elements. This is the sum of the first 1 element, 2, 3, and so on. So let's write 20 plus 20 plus 15 plus 0. If we imagine the first term here, then this would be the sum of the first 5 elements, which is 65. But we want to get rid of this. We want to get rid of the first element because we're not including that within our range. And how do we represent 10? Well, 10 is the sum of the first 1 element, which is this. So to find the sum of second to fifth, and this is inclusive, to find the sum of the second and fifth elements within my base array R, this would be equal to p-sum of 5 minus p-sum of 1. And note that this one comes from 2 minus 1. If I did p-sum 5 minus p-sum 1, I would be getting rid of this thing as well, but I want to keep it. So I would do 1 less than whatever my left bound is. So if I go back here, to find the sum of that range, I would do p-sum of 5 minus p-sum of 1. I'll say 2 minus 1 to make it clear. And if I run that, I should get 55. Okay. All right. There's actually a bit more. I wanted to do the questions, but hopefully you guys learned how these two things work. And I would recommend that you guys start with the LeetCode problems because they're a bit easier than the USACO ones. Because USACO, you have to like read in data and then output stuff, and there's more tricks involved and it takes more time. But yeah, just look over this handout. And once again, the Google Classroom code is this. So join that and I will be posting the handout. I think it should be posted now. Yeah, it says posted now. Yeah, I will turn it over to Tina now for AMC 10.
Oh, okay, thanks. I think you need to make me host or something.
Yeah, sorry. I'm leaving the meeting from my other side.
Oh, also, by the way, Andy,
Yeah.
once like my class is like the last of like everything, right? When I finish, do I just like end the meeting or something?
Yeah, that should work.
All right, all right.
Okay, I've made you host.